Okay, so we're going to prove part of the previous theorem. We're going to prove theorem 0.3 part 1. And that was saying that if given these three sets A, B, and C, A minus the intersection of B and C is equal to A minus B union A minus C. So remember, we have a set on the left equals a set on the right. In order to show that they're equal, one way to do it is as follows. We will show, or you could write it's sufficient to show, or it suffices to show, all we need to do, we will show, number one, that A minus B intersection C is a subset of the right-hand side. And we have to do it the other direction as well. We have to show that A minus B union A minus C is a subset of A minus, in parentheses, B intersection C. So I think I'm going to prove number one, case number one, and let you do case number two, and you can let me know if you have any questions about it. They will be similar. The verbiage will be similar in both cases. Okay, so case one, which I'm going to do. All right, I need to prove that if x is an element of this, then x is an element of the right-hand side. So if x is an element of A minus B intersects C, then what does that mean? Then x is an element of A, and x is not an element of B intersects C. And what we need to get is it's either in this or in that. Okay. It's not in the intersection. Well, what does it mean to be not in the intersection? I'm going to draw a Venn diagram here. It's not part of the proof. I'm going to erase it in a minute. If you're not in this, you could be anywhere else. If you're not in the intersection, you could be anywhere else except in that football-shaped region right there. Okay, so if you happen to be in the circle B, you can't be in C. If you're in C, you can't be in B. You can't be in that region right there. Okay, so you're not in the intersection, you're not in both of them. So, either x is not in B or x is not in C. That's what this statement means. Again, you can draw your Venn diagram to convince yourself of that. If you're not in the intersection, it means you're not in both B and C. You could be in one, but not the other. So it must be true that either you're not in B or you're not in C. Now here's where I'm going to break this case number one into two little cases. That'll be the first case. If that will prove that, and if that happens to not be true, then we know that's true. All right, well, if x is not in B, then x is in A minus B, because we know x is in A. So, if you are in A minus B, then you're clearly in A minus B or something else. So I can just say if x is not in B, then x is in that, and x is in A minus B, and I can put anything I want here, but for this proof I need it to be A minus C. That's the end of our little subcase. Otherwise, if this is not true, then if this is not true, then that's true. Otherwise, X is not in C. Thus, X is in A minus C. It's in A, but it's not in C, so it's in A minus C. And it follows if that's true, then X is an element of A minus B, or A minus C. We know it's in that one. If it's in this one, it's in this or that one. And I'll just say, and we're done. Simple proof, just kind of tearing these sets apart. And again, I will leave case 2 problem for the student. I don't think that's a homework problem. I'm not going to collect it, but it would be worth your writing case 2 out. Assume that you're in this. Let X be an element of this to prove that X is in that as well.